clear, moonless night, the spaces between stars look perfectly black. The darkness feels natural. Stars are distant, scattered, and small, so the light that misses us seems to leave an empty background behind. Yet that familiar picture carries a quiet contradiction. The observable universe contains galaxies beyond easy counting, and each clear patch of sky opens onto an immense depth of cosmic space. Light has been leaving stars in every direction for billions of years. If that luminous population continued without a meaningful boundary in space or time, then every narrow line of sight should eventually meet a stellar surface. Distance would make each star look smaller, but it would also reveal more stars. Under those assumptions, the dark gaps should close. Instead, the night remains mostly black. That blackness is not merely scenery, and it is not explained by saying that stars are far away. It is an observation with consequences. Hidden inside it are limits on how long stars have shone, how light crosses an evolving universe, and what our eyes can detect. Before asking why darkness survives, we have to determine what that darkness actually contains. If this kind of calm, careful journey helps you relax while seeing the universe more clearly, you may like or subscribe for future explorations. For now, let the darkness overhead become not an empty background, but a measurement waiting to be understood. To untangle this mystery, we must first separate the darkness of space from the limits of human sight. Under a clear night sky, our eyes adapt by relying mainly on rods, the light-sensitive cells that work well at low illumination but provide little color and limited detail. Bright stars stimulate small areas of the retina, while much fainter light spread across the sky may never produce a strong enough contrast to look luminous. The result feels like a simple division, sharp points of light set in absolute black. Yet that black is a perception, not a reading of zero. Astronomical detectors tell a subtler story because they can collect photons for minutes, hours, or days. In 1995, the Hubble Space Telescope stared at a tiny northern patch that appeared almost empty. After many exposures was combined, the Hubble Deep Field revealed thousands of remote galaxies. It did not show that every dark patch is packed with equally detectable objects. It showed how much light, ordinary vision, and brief observations leave unrecorded. Even Hubble observes from inside the solar system, where sunlight scattered by interplanetary dust creates zodiacal light. To estimate the still fainter glow beyond our galaxy, astronomers must subtract that foreground along with light from stars, diffuse Milky Way dust, and instrumental effects. The New Horizons spacecraft offers an unusually quiet viewpoint. Far beyond Pluto, where zodiacal light is greatly reduced, its cameras have measured a weak cosmic optical background consistent within present uncertainties, with light accumulated from distant galaxies and perhaps other faint sources. So the darkness between visible stars is not physically blank. It has a measurable surface brightness low, uncertain at the finest level, but not zero. The mystery therefore becomes more exact. We are not asking why no photons arrive. We are asking why the total light reaching us remains so faint. Measuring that faint total is less like photographing an object than listening for a distant note in a room full of quieter noises. A detector pointed away from obvious stars still records light from several layers. Air glow arises when atoms high in Earth's atmosphere emit photons. Unresolved stars and wisps of interstellar dust brighten our own galaxy. Closer still, sunlight strikes dust spread through the plane of the solar system and is scattered into the telescope. This zodiacal light is especially troublesome because it can exceed the extragalactic signal astronomers are trying to isolate. A measurement therefore begins with everything that is not the desired background. Researchers calibrate the camera's electronic response, mask catalogued stars and galaxies when measuring diffuse light, estimate the glow of the Milky Way, and model sunlight scattered by interplanetary grains. Each subtraction carries uncertainty. From near Earth, a small error in the zodiacal model can resemble an unexplained light source beyond all known galaxies. Distance from the Sun changes the balance. New Horizons is now more than 50 times farther from the Sun than Earth is, well outside the densest region of interplanetary dust. Its long-range reconnaissance imager observes selected fields away from the bright Milky Way, while companion data help estimate foreground stars and dust. The remaining optical signal can then be compared with the summed light expected from galaxies too faint or too distant to resolve individually. Recent analyses have narrowed earlier hints of a large unexplained excess. Within current errors, much of the measured cosmic optical background can be accounted for by known galaxies. The exact value remains an active measurement, not a settled number. What matters here is the method cosmic darkness is obtained only after nearby light has been identified and carefully removed. Once those foreground veils are peeled away, the surviving glow is real but extraordinarily slight, leaving our eyes to interpret a weak photon field as black. The eye cannot imitate a camera simply by waiting longer. A digital sensor can preserve each detected photon and add thousands of exposures. The retina must work continuously, adjusting to the light that is present and passing a compressed, changing signal to the brain. After roughly half an hour in darkness, rod cells become remarkably sensitive. Under favorable conditions, a person may respond to only a handful of photons reaching the retina within a small area and brief interval. But that laboratory threshold does not mean every sparse cosmic photon becomes visible as a glowing sky. Detection depends on concentration and contrast. A faint star places light into a compact image, allowing its signal to stand above random fluctuations in the retina. Diffuse extragalactic light is spread over the entire field. Within any one receptive area and moment, its contribution is mingled with air glow, zodiacal light, unresolved galactic light, thermal activity in the eye, and the intrinsic noise of neural signaling. A nearly uniform component supplies no sharp boundary for vision to recognize. The brain treats much of it as the background against which other things are seen. Vision also has to function across an enormous range, from a moonless landscape to a sunlit one. It does not represent each added photon as an equal step in apparent brightness. Adaptation in the retina and later neural processing respond strongly to ratios and local differences, compressing the range of intensities that reaches awareness. At night, rods provide sensitivity, but poor spatial precision and no color. Cones, which give detailed color vision, contribute little at the faintest levels. Thus, a physically busy light field can look serenely empty. Counted over a square meter and over time, the number of optical background photons may be immense, distributed across direction, wavelength, retinal area, and fleeting moments. The signal remains far below ordinary visual surface brightness. Blackness is the brain's practical rendering of insufficient contrast. Instruments replace that rendering with a number, and that number is unexpectedly small beside the amount of luminous matter the universe seems to offer. That comparison turns a familiar sensation into a cosmological test. Astronomers can express the background as radiance energy arriving each second through a given area, from a given patch of sky, across a chosen band of wavelengths. The value is faint, but its importance does not depend on whether an eye can see it. It represents part of the accumulated optical and infrared output of stars and galaxies across cosmic history. Now consider what might have been expected without that history. More distant regions contain more galaxies simply because a larger volume of space comes into view. Their individual sources look dimmer, yet the number available to contribute keeps rising. If roughly the same stellar population extended without end, had been shining forever, and occupied an unchanging universe, adding progressively more remote regions would not allow the total background to settle at the measured low level. Light would continue to accumulate along the sky. This is why the black night is more than a limitation of the retina. Better vision could reveal additional galaxies and a diffuse glow, but it would not erase the enormous difference between that glow and a sky covered by luminous stellar surfaces. The observation tells us that at least one ingredient in the simple picture, endless reach, eternal shining, uniformity, or a static setting cannot describe the real cosmos in the required way. Before deciding which ingredient fails, it helps to accept the old model on its own terms. Strip away expansion, stellar evolution, and any beginning. Let ordinary stars be scattered through an eternal static space with no outer edge, much as many early thinkers once supposed. Then take a single, exceedingly narrow viewing direction and extend it outward. Does it continue forever through empty intervals? Or must it eventually encounter light? The measured night gives one answer. The geometry of that imagined universe appears to give another. Following that disagreement is where darkness becomes a paradox. The old model was never one doctrine adopted all at once. It emerged from attempts to make the heavens stable. In the early 17th century, Johannes Kepler recognized a problem with an infinite field of stars if stars filled endless space in a broadly uniform way. The entire sky ought to shine. He took the dark night as evidence against that particular infinity, though astronomy could not yet supply a modern alternative. Later in the century, Isaac Newton's theory of gravity introduced a different pressure. A finite island of stars seemed liable to collapse under its own attraction, or to possess an unexplained center and edge. Newton suggested that matter spread through infinite space might avoid a preferred center, because gravitational pulls would balance in every direction. That balance is delicate and, as later physics showed, not a stable cosmological solution. Still, infinity offered the conceptual symmetry the mechanical universe appeared to need. Several assumptions became intertwined space extended without boundary. Time had no relevant beginning. The large-scale distribution of stars remained statistically similar from place to place, and the cosmos did not expand or evolve. No astronomer could survey infinity. These were idealizations, reasonable-seeming rules used to ask what a universe governed by familiar geometry and enduring stars should look like. The dark sky difficulty surfaced repeatedly. Edmond Halley and Jean-Philippe de Chaiseau discussed versions of it in the 18th century. Heinrich Wilhelm Olbers gave a widely remembered account in 1823, which is why the puzzle now bears his name, although he neither discovered it first nor supplied the final resolution. Its force comes from consistency rather than history. Grant the classical assumptions and remove all boundaries in distance and duration. Stars need not form a solid wall nearby. They can be extraordinarily sparse. Yet an endless sightline has endlessly many opportunities to meet one. To learn whether the gaps survive, the universe can be divided into a quiet sequence of shells centered on the observer. Choose each shell to have the same modest thickness, like transparent spherical layers surrounding a single point. In a universe with a uniform average density of stars, the nearby shell contains relatively few. A shell twice as far away has a surface area 4 times larger. One 3 times farther has 9 times the area. Because each layer has the same thickness, its volume and therefore its expected number of stars grows approximately with the square of its radius. This does not mean distant space is locally more crowded. Any small cubic region still contains the same average number of stars. There are simply many more such cubes available around a larger sphere. The shell at great distance wraps an enormous area around the observer, so it can hold an enormous population while preserving the same sparse density. Now select a tiny cone of vision rather than the whole sky. Near its tip, the cone encloses little volume. As it extends outward, its cross-section widens with distance, and every equal step in depth samples more space than the step before. If stars are scattered randomly with a non-zero average density, each added interval supplies another chance for the cone to intersect a stellar disk. A miss nearby does not protect the direction farther out. Clustering changes the texture, not the long-range conclusion under the classical assumptions. Stars may collect into galaxies and galaxies into groups, leaving large voids between them. But if this pattern remains statistically similar without limit, A sufficiently long cone passes through endlessly many populated regions. Empty stretches postpone an encounter. They do not create a permanent escape route. The shell construction is powerful because it makes infinity countable one layer at a time. Every finite shell covers only a small fraction of the sky with stars. Yet another shell waits behind it, and another behind that. The crucial question is no longer whether stars are sparse. It is whether the uncovered fraction can remain non-zero after an unlimited number of opportunities for overlap. A sparse forest offers a useful but imperfect way to follow the overlap. Standing among widely separated trunks, one can see open strips between the nearest trees. Farther trunks occupy some of those strips. Still more distant trunks occupy portions of what remains. If a forest continued forever with a roughly steady density and no clearing, the probability of a perfectly unobstructed horizontal line would shrink towards zero. Stars differ from trunks because they are spheres scattered through 3 dimensions, but their projected disks play the same geometric role. Suppose each equal interval of distance has a small chance of intercepting a star along a chosen ray. The chance of surviving one interval is slightly less than 1. Surviving 2 requires missing both. Surviving hundreds requires a long sequence of misses. Multiplying those survival probabilities over unlimited distance drives the remaining clear fraction towards zero, provided stellar size and number density do not themselves fade away. This is a statistical guarantee, not the claim that some particular nearby arrangement covers every direction. At any finite depth, dark gaps remain. Nor must the stars sit in neat rows. Randomness creates unusually empty and unusually crowded paths, but with infinitely many independent opportunities, almost every exact line of sight eventually strikes a photosphere. In mathematical language, the set of rays that escape forever has zero measure under the model. The first star encountered matters because stars behind it are hidden along that ray. The sky is not made infinitely bright by stacking visible stellar surfaces one atop another in the same direction. Instead, the nearest intersecting surface sets the brightness there, just as the first opaque trunk blocks those beyond it. This is the trap in the classical picture. Infinity does not merely provide more pinpoints of light, it gradually removes the spaces between them, taken to its own logical limit. The model replaces a black background scattered with stars by a continuous mosaic of stellar surfaces. The night should not just be brighter than it is, there should be no night-coloured background left at all. A sky tiled by stellar surfaces would possess their surface brightness. This distinction is easy to miss. A distant sun-like star delivers little total light because its apparent disk is tiny. But within that tiny disk, ordinary Euclidean geometry does not make each visible patch intrinsically dimmer with distance. Distance reduces the received flux and the apparent solid angle by the same factor, leaving brightness per unit solid angle unchanged. If such disks covered the sky, the combined view would resemble the radiating surfaces themselves. Not every star has the sun's temperature or luminosity, so the exact spectrum would be a population-weighted mixture rather than a perfect copy of the solar photosphere. Cooler red stars would contribute differently from hot blue ones. Even so, an eternal static universe filled indefinitely with ordinary stars predicts a brilliant thermal sky. Broadly comparable in surface brightness to a stellar atmosphere, not the faint optical background actually measured. Earth could not simply enjoy normal daylight around the clock under that radiation. Energy would arrive from nearly every direction, heating matter until it approached equilibrium with the surrounding light field. The familiar division between a bright solar disk and a dark celestial background would vanish. Calling this result absurd does not mean the mathematics has failed. It means the assumptions have produced an observational consequence that nature plainly refuses. The conflict is Olber's paradox in its sharp form and endless, eternal, statistically uniform, static stellar universe should erase optical darkness, while the real sky remains overwhelmingly dark between resolved sources. something prevents most possible sight lines from ending on visible stellar photospheres, or reduces the radiation reaching us in a way absent from the model. The first refuge of intuition is distance. Perhaps those remote surfaces are present but too faint to matter. Yet the argument has already hinted at why that answer is incomplete. Shrinking brightness arrives beside expanding numbers and shrinking angular size. To see the cancellation cleanly, we must follow not merely where a sightline ends, but how much light every successive shell contributes. Distance certainly dims an individual star. If a star radiates luminosity L equally in all directions, its light at radius r is spread over a sphere whose area is 4 pi r squared. A detector intercepts only a small portion of that sphere, so the received flux is L divided by 4 pi r squared. Move the same star twice as far away and its flux falls to 1/4. At 10 times the distance, it falls to 1/100th. This inverse square law agrees with ordinary experience. A nearby lamp appears brighter than an identical lamp far down a road. In astronomy, it explains why even extremely luminous stars can look modest across interstellar distances. It is therefore tempting to apply the rule to the whole universe. In one sentence, sufficiently remote stars must become negligible, and darkness is simply what remains. The mistake lies not in the law but in what is being counted. The inverse square relation describes one source held in isolation. Olber's paradox asks about an entire population whose available number changes with distance. Moving outward does not keep the sample fixed. It opens larger spherical layers containing progressively more stars. There is another subtlety. A star twice as distant sends us 1/4 of the flux, but its apparent disk also covers 1/4 of the solid angle. Its surface brightness, the flux received per apparent area, therefore remains the same in a static Euclidean universe with no absorption. The star becomes smaller, not grey. Telescopes reveal this distinction whenever an extended object retains its brightness per patch, while shrinking with distance apart from instrumental blurring. For a finite collection, distance can make the total light as small as expected. For an infinite, uniformly replenished collection, it cannot be considered alone. Every weakening factor must be compared with the growth in source count. The next shell supplies exactly the arithmetic needed. One radius squared dims each star, while another radius squared multiplies how many stars are there. Take a thin shell at radius r with thickness d. Its volume is approximately 4 pr squared times d. If the average number density of stars is n, then the shell contains about n multiplied by that volume. The expected star count therefore rises as r squared, exactly because the shell's spherical area grows that way. For clarity, first suppose every star has the same luminosity L. Each one supplies flux L divided by 4 pr squared. Multiply that flux by the number in the shell n times. 4 pr squared doctor times L divided by 4 pr squared. Both 4 pi and r squared cancel. What remains is simply nl doctor. The shell's total contribution does not depend on its radius. A layer 1,000 times farther away contains roughly 1,000,000 times as many stars, while each star is roughly 1,000,000 times fainter. In this ideal Euclidean model, those changes balance exactly. A more realistic range of stellar luminosities changes L into an average luminosity, but leaves the cancellation intact as long as the population is statistically steady. Thin shells also make clear what the calculation is and is not claiming. It describes light before accounting for one star hiding another, and before adding absorption, cosmic expansion, stellar births, or a finite travel time. Those effects are precisely the assumptions that later need examination. Over distances where overlap is still small, the shell sum shows why flux accumulates linearly with depth rather than fading away. There is no privileged radius beyond which geometry suddenly wins on behalf of darkness. Each additional equal thickness contributes the same expected amount as the one before it. A finite universe provides only finitely many layers, so its sum can remain finite and faint, An infinite model offers no final layer. The arithmetic keeps adding equal terms, which turns the comforting inverse square law from an apparent solution into one half of an exact cancellation. The cancellation changes the meaning of remoteness. No individual far shell overwhelms the nearby universe. Each is only one equal contribution. The difficulty appears when the model supplies an unlimited sequence of them. One equal amount of radiance, added again and again without a last term, cannot approach a small fixed total. If stars were transparent points, the formal sum would diverge twice. The surveyed depth would give roughly twice the flux. An infinite depth would imply unbounded illumination. Real stars are opaque bodies with finite disks, so that literal divergence cannot continue forever. As the layers accumulate, foreground stars hide increasing numbers behind them. The calculation then approaches the complementary picture developed earlier. Instead of limitless visible stacks, the sky becomes covered, and its brightness approaches the characteristic surface brightness of the first stellar photosphere along each direction. These are not competing versions of the paradox. They describe two stages of the same geometry. Before overlap matters, equal shells make the background brighten in proportion to path length. Once overlap dominates, additional distance light is blocked, but only because luminous surfaces have already filled nearly every direction. Either route rules out a persistently black background. The result also explains why moving the imagined boundary farther away never resolves the problem. A boundary at a finite distance can leave the sky faint if too few shells lie inside it. Push that boundary outward, and the light grows. Remove it altogether while keeping the stellar density and luminosity unchanged, and darkness loses its mathematical protection. The deeper cognitive shift is simple distance redistributes light. It does not selectively erase the integrated output of an endless uniform population. The same spreading that weakens one source allows a spherical layer to contain more sources in exact proportion. To recover the sky we observe, some additional physics must limit the number of contributing shells, change their luminosity through time, alter photons during their journey, or prevent starlight from reaching us. Pure Euclidean distance has exhausted what it can do. Once distance is removed as the answer, the paradox becomes a test of premises. Perhaps stellar matter does not continue with a steady average density to unlimited depth. Perhaps stars have not shone for an unlimited past. Perhaps space changes while photons travel, so the classical inverse square bookkeeping is incomplete. The real universe uses more than one of these departures, but geometry alone cannot tell us which. It can, however, prevent easy evasions. Making stars smaller merely increases the typical distance a ray travels before meeting one. Over infinite depth, the chance of escape still tends towards zero. Making stars rarer has the same effect, unless their average density falls sufficiently with distance, which abandons uniformity or introduces a special location. Rearranging them into galaxies creates dark intervals, but an endless, statistically repeating hierarchy still offers endlessly many luminous regions. A curved static geometry might alter the details of areas and volumes, yet curvature by itself is not a general guarantee of a dark, eternal sky. Any successful model must make the integrated radiative contribution converge or keep stellar surfaces from covering the available directions. That requires a genuine physical limit, not the verbal assurance that remote things look faint. The most immediate proposal is to place something in the way. Real astronomical images contain dark nebulae, lanes of dust, and cold molecular clouds that plainly hide stars behind them. Intergalactic space also contains gas and dust. If enough opaque material lies along long paths, perhaps it could intercept each shell's light before the light reaches us, preserving a dark foreground even in the eternal model. That suggestion changes the problem from geometry to energy. A cloud can remove visible photons from one direction, but it must do something with the energy it absorbs. In a universe illuminated forever from all sides, An absorber cannot remain permanently cold and black without an unlimited sink. The next apparent solution therefore asks a deeper question. Can matter hide eternal starlight, or does the hidden light eventually make the matter shine? Dark clouds seem to offer exactly the missing screen. Through a small telescope, the Milky Way contains ink-dark patches where background stars disappear. In visible light photographs, dust lanes divide bright galaxies, while dense molecular clouds can conceal newborn stars almost completely. If ordinary matter can erase light so effectively nearby, an unlimited succession of such barriers might appear able to protect the night from an unlimited succession of stars. Versions of this idea accompanied early discussions of the paradox. 18th and 19th century writers, including the astronomers whose work led to the puzzle associated with Olbers, considered whether obscuring material could weaken radiation from great distances. The proposal was physically natural. Astronomers already knew that some regions of the sky contained fewer visible stars, even before the absorbing role of interstellar dust was understood in modern terms. The real universe does contain the required ingredients. Tiny solid grains made largely of silicates and carbon-rich material scatter blue light and absorb a broad range of stellar wavelengths. Atoms and molecules absorb selected frequencies. A sufficiently thick cloud can reduce optical starlight by enormous factors. But this explains why one region looks darker than another. It does not yet explain why an eternal universe is dark as a whole. Dark matter does not supply a better curtain. Despite its name, the evidence indicates that it interacts extremely weakly with electromagnetic radiation. Light generally crosses dark matter halos without being absorbed, although their gravity can bend and magnify it. Ordinary gas and dust are the serious absorbers, and any absorber creates an accounting problem. Scattering merely redirects photons, so light removed from one sight line emerges along others. Absorption is different, but it is not disappearance. The photon's energy enters the material, usually as internal motion and heat. A finite cloud can remain cool when it gains and losses balance. A cloud exposed to eternal starlight from every direction must keep accepting energy until its own radiation can answer the incoming flow. The proposed screen is therefore not simply an obstacle. It is a body being steadily warmed. The warming begins at the microscopic level. An optical photon absorbed by a grain excites its electrons or sets its lattice vibrating. Collisions rapidly share that energy among many internal motions, converting a directed beam into heat. The first law of thermodynamics leaves no option for silently deleting the energy. It can be stored for a while, used in a chemical or structural change, or released again. Storage cannot continue forever in an unchanging universe. As a grain gains energy, its temperature rises. All matter above absolute zero emits electromagnetic radiation, and warmer matter emits more power. For an ideal black body, the radiated power per unit area rises with the fourth power of temperature. Real dust is not a perfect black body, but the same feedback remains. Heating strengthens its emission until energy leaves as quickly as it arrives. This is visible in our own galaxy. A dark nebula may be nearly opaque at blue and visible wavelengths, yet glow clearly in infrared images. Its grains absorb energetic photons from nearby stars, then emit many lower-energy infrared photons. The cloud has not removed luminosity from nature. It has changed the directions and wavelengths in which that luminosity travels. Kirchhoff's law makes the connection precise. At any wavelength, a material that absorbs efficiently is also an efficient thermal emitter under equilibrium conditions. A perfectly black screen is therefore not a surface that can remain black while being irradiated forever. Its very ability to take in radiation gives it the ability to radiate. The second law sets the direction of the approach. Net heat flows from a hotter radiation field toward colder matter. As the matter warms, that imbalance diminishes. It cannot continuously transfer the absorbed energy into an environment already sharing its temperature. nor maintain a colder state without some separate reservoir. In the classical eternal cosmos, there is unlimited time for the transient warming to end. The question then becomes what the screen looks like after absorption and emission have reached balance. At balance, the word dark becomes misleading. Consider a grain surrounded by a steady radiation field. If it absorbs more power than it emits, it warms. If it emits more than it absorbs, it cools. Its stable temperature is the one at which those rates are equal. Each second, the grain then returns to space as much energy as it receives. The outgoing spectrum need not resemble the incoming spectrum photon for photon. Hot stars send much of their radiation at visible and ultraviolet wavelengths. Cooler dust radiates mainly in the infrared, producing more photons of lower individual energy, yet the total power is conserved at equilibrium. Obscuration can redden the sky or move its brightness outside human vision. It cannot make an eternal energy supply vanish. Now extend the argument through many clouds. The first cloud absorbs radiation from stars behind it and re-radiates. A second cloud can absorb that infrared emission, but it too warms and emits. Repeating the transfer does not create a terminal layer where energy is permanently lost. Given unlimited time, matter and radiation approach a common thermal state, with the exact spectrum depending on composition and on the surrounding field. There is an important qualification. The equilibrium temperature of dust is not generally equal to a star's photospheric temperature. It depends on how intense the ambient radiation is and how efficiently grains absorb and emit at different wavelengths. In our actual dilute, evolving universe, most interstellar grains remain cold because their received power is modest and their infrared radiation escapes. The claim concerns the old model's unlimited illumination and unlimited duration. Under those assumptions, dust cannot remain a cold foreground indefinitely. If the stellar sky would otherwise deliver a high radiative intensity, the dust must ultimately return the same power, whether in visible light or at longer wavelengths. Human eyes might still call the shifted field dark, but a bolometer would not. The paradox has survived in a broader form, not merely why the optical sky looks black, but why the total cosmic radiation field is so weak. Every spatial barrier therefore fails for the same reason it delays or transforms light without supplying a final sink. An opaque cloud blocks a star but becomes a radiator. A chain of clouds passes energy outward in new wavelengths. Finite stellar disks prevent infinite stacks along one ray, but only by filling that ray with the bright surface of the nearest star. None preserves a weak radiation field inside an eternal, steady source population. One might let dust be destroyed after absorbing enough energy. Grains can evaporate, molecules can break apart, and gas can become ionized, but these processes consume only finite amounts of energy. Once the material changes state, continued illumination remains. To keep the sky dark forever, the model would need an inexhaustible mechanism that removes energy without warming or radiating an added physical assumption far more mysterious than the darkness it was meant to explain. This does not make cosmic dust unimportant. In the real universe, it strongly reshapes what telescopes see, hides young stars, and converts a large portion of stellar light into infrared emission. Nor does it imply that every obscuring cloud has already reached perfect equilibrium. Stars and clouds form, change, and disperse. Their transient temperatures are evidence that cosmic conditions are not eternal and static. That is precisely the clue. All the failed screens were granted unlimited time. Their failure follows because unlimited exposure erases their initial coldness. Remove that duration, and the conclusion changes. A cloud illuminated for only a finite interval may still be cool. More importantly, light from sufficiently distant stars may not have had time to arrive at all. The successful boundary need not be a wall at the edge of space. It can be a boundary in the past. If stars began shining at finite times and light travels at finite speed, then looking farther outward also means looking farther backward. Beyond some depth, a sightline does not encounter older and older active stars. It reaches epochs before their light existed. The dark sky is leading us away from hidden matter and toward travel time. Light makes distance a record of time. The moon appears as it was a little over a second ago. The sun, roughly 8 minutes ago. The nearest large galaxy, more than 2 million years ago. No telescope sees a remote object in a universal present. It receives an old signal that has spent part of cosmic history in flight. The finiteness of that speed first became measurable on an astronomical scale. In the 1670s, Ole Rømer studied eclipses of Io, a moon of Jupiter. Their apparent timing shifted systematically as Earth moved closer to or farther from Jupiter. Rømer correctly inferred that light needed additional time to cross the changing distance. His estimate was imperfect, but the conclusion was decisive. Light does not arrive instantaneously. That fact inserts a temporal limit into the shell argument. A shell 1 billion light-years away can contribute only radiation emitted at least 1 billion years before the observing moment. A still more distant shell must be sampled at a still earlier epoch. If the luminous era has a finite duration, adding distance eventually stops adding ordinary stars as they exist now. The sightline outruns their history. Edgar Allan Poe expressed a striking version of this insight in his 1848 prose poem Eureka. He suggested that stars might be so distant that their rays had not yet had time to reach us. Poe's cosmology was not modern scientific's theory, and the resolution involves more than this one idea. Yet he identified the central escape from an eternal sky darkness can mark information still absent because propagation takes time. A finite light speed alone is not enough. If stars and the universe had existed eternally, even slow light would have had an unlimited past in which to arrive. What matters is the combination. Light has a finite speed, and the cosmos has a finite age with a finite history of stars. Together they replace endless contributing shells with a bounded record of luminous time. Modern cosmology gives that record a scale. The universe is about 13.8 billion years old, measured through several mutually supporting observations, including its expansion history, the cosmic microwave background, and the ages of old stellar populations. No signal can have travelled through the universe for longer than the universe has existed. The resulting limit is called the particle horizon, the present boundary of regions from which light or any causal influence could have reached us since the early universe. It is not a physical shell made of matter, and it is not a place where space necessarily ends. There may be vastly more cosmos beyond it. We simply have not been in causal contact with those regions. A common shortcut says that the observable universe has a radius of 13.8 billion light-years, because light has travelled for 13.8 billion years. That would be true in a static space. Cosmic space expanded while the light was in transit. The matter that emitted the oldest light we receive has continued to recede, so its present proper distance is roughly 46 billion light-years in the standard cosmological model. The observable diameter today is therefore about 93 billion light-years. These numbers describe different questions, not conflicting measurements. Look-back time asks how long a photon has travelled. Present distance asks how far away its source region is now, measured on a chosen cosmic time slice. Co-moving distance labels the separation after factoring out the general expansion. For Olber's paradox, the essential quantity is the finite interval available for radiation to propagate and for stars to shine, not a simple static radius. There is also an earlier observational boundary. For roughly the first 380,000 years, the universe was an opaque plasma in which photons scattered repeatedly from charged particles. The oldest electromagnetic light visible directly today comes from the later transition to transparency and now arrives as microwaves. Ordinary stars formed later still. Thus, the accessible past is not filled uniformly with stellar surfaces. The horizon limits how far causation reaches. while cosmic history limits what kinds of luminous objects exist at each depth. Seen this way, a dark gap is not a ray that wanders forever through present-day empty space. It is a path into earlier conditions. Nearby along that path, it may miss stars by chance. Farther away, it samples galaxies at younger stages. Farther still, it reaches eras before any stars had formed. Continuing backward encounters hot primordial matter, not an eternal repetition of the modern stellar population. This breaks the geometric guarantee at its temporal foundation. The classical calculation assigned every shell the same average luminosity and allowed infinitely many shells to contribute. The real calculation cannot do that. Each shell corresponds to a different emission time, and the sequence ends at a finite cosmic past. Its luminosity density also changes. There was a dark age before the first stars, followed by a developing population rather than steady lights shining forever. It is tempting to call the night sky direct proof that the entire universe began a finite time ago. The conclusion needs care. Darkness alone does not uniquely determine a cosmological model. A suitably declining stellar density or other changes could also make the light integral finite, but it decisively rejects the particular combination of eternal duration, static geometry, and an unchanging stellar population. Together with independent evidence, it becomes a visible consequence of cosmic age. Nor do sightlines beyond a static distance of 13.8 billion light-years simply hit a black wall. Because space expands, we observe galaxies whose present distances are much larger, while seeing them at ancient look-back times. Beyond the stellar era, the universe was not empty, and its surviving early glow will matter later. It is simply not a sky of optical photospheres. The blackness between stars is therefore incomplete coverage in time. The universe has not had long enough to populate every angular direction with the accumulated output of eternal suns, and stars themselves have not existed for most conceivable past time. What looks like absence is partly a historical limit to the finite archive of light that has so far reached this one event called here and now. Finite age does most of the conceptual work, but it does not act alone. Even within the horizon, photons do not cross a rigid Euclidean stage. The distances between widely separated, unbound galaxies change during the journey. The universe that receives an ancient photon is larger than the universe in which that photon was emitted. This matters because a finite-age static model and an expanding model can have the same available travel time yet deliver different background intensities. In the static case, every photon that reaches us retains the wavelength and energy set at emission, aside from local interactions. Expansion changes both the photon's observed energy and the rate at which a stream of photons arrives. Remote luminous history is therefore not merely truncated, its contribution is diluted in transit. Expansion also complicates the language of motion. Galaxies participate in a changing cosmic geometry, with average recession speed increasing with distance according to the Hubble-Lemaitre relation nearby. They are not generally racing through pre-existing empty space from one central explosion. On large scales, the metric used to measure separation evolves, and every unbound region sees broadly the same pattern. The finite horizon and expansion are related but distinct. Age limits how much past light can be present at all. Expansion weakens much of the light that is present. Stellar evolution adds another distinction. Sources did not shine steadily across the entire available interval. A complete explanation of darkness combines all three, rather than searching for one slogan. The next step is to accompany a single wave crest from a distant galaxy. At emission, its spacing may place it in visible blue or green light. While the photon moves locally at the invariant speed of light, the cosmic scale factor grows. By arrival, successive crests are measured farther apart. Nothing has intercepted the beam, yet its color and energy have changed. The journey itself has become part of the explanation, and the darkness of visible space now depends not only on whether light arrives, but on what expansion has made of it. Take two successive crests of that ancient light wave. As they leave a galaxy, the distance between them defines the emitted wavelength. During billions of years of travel, both move locally at light speed, but the large-scale geometry through which they pass evolves. By the time they reach us, their measured separation is greater. The wave has been cosmologically redshifted. Astronomers describe the effect with the redshift as 1 plus S equals the observed wavelength divided by the emitted wavelength. If a spectral feature emitted at 500 nanometers is observed at 1000 nanometers, its wavelength has doubled and Z equals 1. More generally, that same factor equals the cosmic scale factor now divided by the scale factor at emission. This is related to the Hubble-Lemaitre law, which says that nearby galaxies, on average, recede faster the farther away they are. For modest distances, their spectral redshifts track that recession approximately. At cosmological distances, however, redshift records the full expansion history during the photon's journey. It is not adequately described as a single ordinary Doppler velocity through static space. Bound systems resist this general stretching. Atoms do not expand. Earth does not grow with the scale factor, and gravity keeps the Milky Way and nearby galaxies together. Expansion is evident across sufficiently large separations where matter is not held in a common bound structure. A photon crossing those scales links an earlier, smaller scale factor to the larger one measured at reception. It is useful to say that its wavelength stretches with the universe, provided the phrase is not mistaken for friction or repeated collisions. The photon can travel through transparent space without being absorbed. Its changing wavelength arises from how distant emitters and observers compare intervals in an evolving space-time. The result is nevertheless physical and measurable. Familiar atomic lines arrive displaced toward the red, and the farther past is generally carried to us on longer waves. Longer wavelength means lower energy per photon. Quantum mechanics gives that energy as h times the speed of light divided by wavelength. If expansion doubles a photon's wavelength, the receiving detector measures half the energy that an otherwise equivalent local photon would carry. In redshift notation, each photon's observed energy is reduced by a factor of 1 plus Z. A second reduction comes from timing. Suppose a distant star emits two successive wave packets separated by 1 second in its local frame. The expansion that lengthens their wavelengths also lengthens the interval between their arrival. At redshift 1, a sequence emitted over 1 second is observed over 2 seconds. The same number of photons is spread across more receiving time, so the measured power falls by another factor of 1 plus Z. Together, these two effects reduce the received bolometric energy rate by a factor of 1 plus Z squared, before accounting for geometric spreading through the appropriate cosmological distance. One factor belongs to energy per photon, the other belongs to the arrival rate. This is why a remote source can be more strongly diminished than the classical inverse square picture suggests. For an extended source, two further geometric factors enter when comparing surface brightness. Its apparent area and the relation among cosmological distance measures lead to the Tolman dimming law, bolometric surface. Brightness falls as 1 plus Z to the 4th power in an expanding universe. The distinction matters. The double factor describes redshift and time dilation in the energy stream. The 4th power describes the full observed surface brightness reduction. None of this means photons gradually slow below light speed. Every local observer in vacuum measures light at c. The longer arrival interval reflects stretched temporal separation between successive signals, not slower local motion. Nor is it ordinary absorption, because the photon count along an unobstructed beam can remain intact, while each photon arrives less energetic and the sequence less frequently. Expansion weakens ancient starlight twice before human vision even decides whether its shifted wavelength is visible. Visibility adds a biological boundary to the physical losses. Human eyes respond to only a narrow band, roughly from violet near 400 nanometers to deep red near 700 nanometers. with sensitivity varying across that range. A photon can arrive at Earth and still make no contribution to sight because its wavelength lies beyond those limits. Consider ultraviolet light emitted at 250 nanometers by hot young stars. From a galaxy at redshift 3, 1 plus z is 4, so that feature reaches us near 1000 nanometers in the near-infrared. Visible light emitted at 500 nanometers from the same redshift arrives around 2000 nanometers, farther into the infrared. Nothing has extinguished those photons. A detector designed for longer wavelengths can record them, while an unaided observer sees black. At still larger redshifts, radiation that began in the ultraviolet or visible is carried through infrared bands and, given sufficient expansion, toward microwave and radio wavelengths. The shift is continuous rather than a sudden crossing into an invisible realm. Different instruments assemble different slices of the same travelling radiation field. Intervening matter also shapes the spectrum. Neutral hydrogen efficiently absorbs photons shortward of particular ultraviolet transitions, producing the Lyman alpha forest and, at high redshift, a strong break in a galaxy's observed colours. Dust can absorb optical light and re-radiate it in the infrared. These effects work alongside cosmological redshift, but they should not be confused with it. The cognitive reversal is that an optically dark sky need not be radiation poor at every wavelength. Ancient luminous processes can survive around us as infrared, microwave, or radio backgrounds, weakened and translated beyond retinal sensitivity. Expansion, therefore, helps explain why visible starlight does not accumulate as the classical model predicted, but it also warns against equating invisibility with non-existence. The universe can look darker to an eye precisely because so much of its oldest light has been carried into forms the eye never evolved to register. Has the missing photon energy been destroyed? In an expanding space-time, that question cannot always be answered by imagining a universal box with a fixed total energy. General relativity guarantees local conservation of energy and momentum emission, absorption, and every local interaction balance. But a changing cosmological geometry generally lacks the time translation symmetry needed to define one conserved global energy for all space. Thus, the lower energy measured for a redshifted photon is real, yet it need not have been deposited in a hidden medium. In simple cosmological language, its energy decreases as the scale factor grows. One can describe work-like exchanges with the expanding geometry in particular formulations, but there is no unique reservoir in which every lost joule accumulates. This is a property of curved, dynamic space-time, not a violation of a local physics. Expansion also does more than conceal light from human eyes. A redshifted photon outside the visible band can still be detected, but it carries less energy than at emission, and successive photons arrive more slowly. Even a perfect all-wavelength instrument would measure a diluted radiation field. Optical biology adds another layer of darkness. It is not the whole cause. We can now state the partial resolution cleanly. Finite age prevents infinitely many luminous shells from contributing. Cosmic evolution means those shells were not equally rich in stars. Expansion reduces the energy and arrival rate of the radiation that does reach us, while moving much of it beyond visible wavelengths. Together, these departures dismantle the eternal static prediction. Yet one question has merely moved upstream. Redshift can weaken light already produced, but how much light could stars ever produce in the first place? Stars are not permanent lamps. Their luminosity comes from finite reservoirs of nuclear fuel, and the fraction of cosmic matter that becomes luminous is limited. To understand why space never approaches a stellar furnace, even before every propagation loss is counted, the photon budget must begin inside the stars themselves with mass, fusion, and the brief eras during which the universe turns fuel into light. Inside a star, brightness begins as a small deficit of mass. In its core, 4 hydrogen nuclei can ultimately become 1 helium nucleus through a chain of reactions. The helium product and other particles have slightly less mass than the starting ingredients. That difference emerges as energy, first carried by radiation and elusive neutrinos, and later, after a complicated passage through the star, as the light and heat escaping its surface. Einstein's relation, E=mc², makes a little mass energetically valuable, but ordinary hydrogen fusion does not convert an entire star into radiation. The mass difference between the initial hydrogen and final helium is about 0.7%. Some energy leaves in neutrinos, and only the material reaching sufficiently hot, dense burning regions participates at a given stage. Much of a star's mass remains outside its active core, while later fusion reactions yield progressively less energy per unit mass as nuclei approach iron. Nor is every cosmic ingredient available as fuel. Most matter is dark matter, which shapes galaxies gravitationally, but is not known to undergo stellar fusion. Ordinary, or baryonic, matter accounts for only about 5% of the universe's total energy density today. Much of that ordinary matter lies in diffuse gas outside stars. Some is locked in remnants, planets, or cool objects. Across cosmic history, only a limited fraction has passed through luminous stellar interiors. An infinite spatial universe could contain infinitely many stars overall, and still provide only a finite amount of usable nuclear energy within any finite volume and any finite causal past. What controls the local radiation field is not the abstract total beyond all horizons, but the density of fuel, the rate at which it burns, and the time its photons have had to arrive. Stars are therefore reservoirs with valves, not permanent fixtures. Their masses may be immense, yet their accessible fusion accounts are bounded. Once a star begins making light, its luminosity measures how quickly that account is being spent, and that spending rate determines how long the lamp can remain on. A star's balance between reservoir and spending rate can produce different lifetimes. The most massive stars consume fuel with extraordinary intensity. Although they begin with far more mass than the Sun, their luminosities rise so steeply that some leave the main sequence after only a few million years. They end quickly, returning enriched gas to space, and leaving a remnant rather than an enduring source. A star like the Sun burns more economically and remains on the main sequence for roughly 10 billion years. Low-mass red dwarfs are thriftier still. They mix a larger share of their hydrogen into regions where it can fuse and radiate slowly. The smallest hydrogen-burning stars may persist for trillions of years, far longer than the universe has existed so far. None has yet reached the end of such a lifetime. Trillions of years sounds almost eternal beside human experience, yet it remains finite, and it is remarkably short beside the duration required for a sparse universe to acquire a photosphere-bright radiation field. The astronomer Edward Harrison developed this energy-based view of Olbers's paradox. With representative stellar luminosities, sizes, and cosmic densities, estimates of the time needed for starlight to build toward the classical bright sky condition can be of order 10 to the 23rd years. The exact figure depends on the model. Its significance lies in the gap of many orders of magnitude. The universe is not merely younger than that filling time. Its stars also do not shine continuously throughout it. Massive stars switch off. Gas cycles through generations, and even red dwarfs eventually exhaust usable fuel. Light escaping into expanding space is meanwhile redshifted and diluted rather than stored in a static cavity. Stellar longevity therefore cannot rescue the eternal lamp assumption. A long-lived red dwarf extends one account. It does not remove the account's limit, compared with the time a dilute stellar population would need to saturate the sky. Every kind of star is temporary. The relevant question now is not whether individual stars can last, but whether all available stars, taken together, contain enough convertible energy ever to pay the much larger radiative cost. Adding the accounts changes the scale, but not the arithmetic. Begin with the cosmic mean density. In the standard model, baryons, protons, and neutrons in gas, stars, and other ordinary matter supply about 5% of the present critical energy density. Dark matter contributes substantially more mass, yet offers no established nuclear furnace. Dark energy is not stellar fuel at all. Now narrow the baryonic share. Only a minority of ordinary matter is locked in stars today. Of the material inside stars, only part reaches fusion conditions, and hydrogen to helium burning releases about 7/1000ths of the reacting rest mass. Some of that release escapes as neutrinos rather than background starlight. Successive filters therefore separate the full mass energy density from the much smaller amount ever available as stellar radiation. This creates a useful thought experiment. Suppose every accessible star were allowed to complete its luminous history, and every stellar photon could be gathered without redshift or absorption. The resulting energy per cubic meter would still be finite because the usable fuel per cubic meter is finite. Spreading that output through the enormous volume between stars cannot reproduce a radiation bath whose intensity resembles a stellar surface. Expansion and losses make the actual result fainter still. The phrase "the universe is full of stars" hides this distinction between abundance and filling factor. Galaxies can contain hundreds of billions of stars while occupying a cosmos whose average density is extremely low. Bright structures are concentrated into small regions separated by vast volumes. Infinity, if space is infinite, repeats that finite average density. It does not place infinite energy inside our local cubic meter or our finite past light cone. Darkness is therefore not surprising once the budget replaces the star count. The classical paradox granted each region a steady luminosity for unlimited time, allowing a finite power density to accumulate without limit. Real stars offer finite energy density over finite history. Their combined output can make a measurable extragalactic glow, but not a photospheric sky. And that output was not produced at a constant rate. The cosmic furnace rose, peaked, and has already begun to quiet. That rise can be reconstructed by surveying galaxies at different look-back times. Astronomers estimate how rapidly each epoch formed new stellar mass per unit cosmic volume, correcting as carefully as possible for stars hidden by dust. Plot the result against time, and the history resembles a broad mountain rather than a level plain, the relation often summarized by the Maddow-Dickinson curve. After the first generations ignited, star formation accelerated as growing galaxies gathered cold gas. It reached its broad maximum during cosmic noon, around redshift 2, when the universe was roughly 3 to 4 billion years old. Per unit volume, stars were then forming several times faster than they do nearby today. The exact height and shape depend on observations and dust corrections, but the overall rise and decline are well established. Since that era, expansion, heating, stellar feedback, and the consumption or expulsion of cold gas have reduced the average formation rate. Stars still form in the Milky Way and countless other galaxies. The furnace has not gone out, but the present universe is past its most prolific phase. Looking outward therefore samples neither a fixed density of eternal lamps nor a simple sequence in which every shell resembles our neighborhood. It crosses a luminosity history with a beginning, a crest, and a fading side. This history also explains why generations matter. Short-lived massive stars dominate ultraviolet output, enrich their surroundings, and disappear. Longer-lived stars preserve earlier episodes, while dust absorbs part of their light and re-radiates it in infrared. The extragalactic background is the softened, red-shifted sum of these changing populations, not brightness accumulating at one rate forever. A night sky can thus be rich in stellar memory while remaining optically black. Its faint glow records a temporary conversion of limited gas during a limited age. But stars are not the oldest radiation available. Before any stellar generation, the universe itself was hot enough to shine everywhere. That ancient light still fills space, transformed so completely in wavelength that eyes beneath a dark sky cannot see it. Give the night sky a different kind of eye and its appearance changes. An infrared detector finds warm dust and red-shifted galaxies where vision reports nothing. a radio receiver hears energetic events and cold gas. Most pervasive of all is a microwave signal arriving from nearly every direction, so uniform that it cannot be assigned to a collection of ordinary stars. In 1964, Arno Penzias and Robert Wilson were preparing a sensitive horn antenna for radio astronomy at Bell Laboratories. An unwanted background remained after they accounted for the receiver. The atmosphere, known celestial sources, and even debris in the antenna. It did not follow the daily motion of an object in the sky. The excess was approximately isotropic wherever the antenna looked. A similar microwave noise persisted. At nearby Princeton, researchers were preparing to search for relic radiation predicted by hot universe cosmology. The two efforts met, and the unexplained antenna temperature was recognized as evidence of the cosmic microwave background. Penzias and Wilson had not made the first theoretical prediction, nor were they initially seeking the early universe. Their careful, unwanted signal became the observation. Later spacecraft turned that background into a precision sky. COBE established its extraordinarily accurate thermal spectrum and detected tiny directional variations. WMAP mapped those variations in greater detail, and Planck refined measurements across multiple frequencies. After foreground emission from the Milky Way is modelled and removed, the maps show a near-uniform field patterned with temperature differences of only tens to hundreds of millionths of a Kelvin. These images do not mean the microwave sky would dazzle a human retina. Microwave photons do not trigger our photoreceptors, and the energy flux is gentle by everyday standards. Yet an instrument tuned to those wavelengths finds no empty backdrop. Behind galaxies, dust, and local radio sources lies an all-sky thermal glow. The next question is how a universe that now appears cold and black came to contain radiation with the unmistakable spectrum of heat. To find the source of that heat, the cosmic film must run backward. As the scale factor decreases, wavelengths shorten and radiation grows hotter. Matter also becomes denser. In the universe's first hundreds of thousands of years, ordinary atoms could not remain assembled. Energetic photons continually separated electrons from nuclei, leaving a hot, ionized plasma. That plasma was opaque in a particular sense. Photons did not travel freely over cosmological distances. They scattered repeatedly from free electrons, changing direction and maintaining near thermal equilibrium with matter. Looking farther back with light would therefore be like looking into glowing fog. There was radiation everywhere, but no clear view through it. As expansion continued, the temperature fell to roughly 3,000 Kelvin. Around 380,000 years after the Hot Big Bang, electrons could remain bound mainly to hydrogen and helium nuclei. This transition is called recombination, although it was the first durable combination for most particles. With far fewer free electrons available for scattering, the universe became transparent, and photons began streaming across space almost unhindered. Those photons form the cosmic microwave background. The surface from which they last scattered surrounds every observer, because looking in any direction looks backward to the same transparent transition, not because Earth occupies its center. At release, the radiation had a thermal spectrum associated with about 3,000 Kelvin. Since then, cosmic expansion has lengthened its wavelengths by a factor of roughly 1/100. The temperature of freely traveling blackbody radiation falls inversely with the scale factor. The relic spectrum is therefore observed today at about 2.725, Kelvin usually rounded to 2.73, peaking in the microwave range rather than visible light. Expansion did not simply place a veil in front of the stars. It transformed an almost uniformly glowing early sky into a cold microwave field. The glow is present throughout intergalactic space, not painted on a nearby shell. Any observer moving with the cosmic expansion would measure a similar background, with small local and directional differences. To understand how something so cold can dominate the universe's photon count, we must count photons rather than judge them by the energy of each one. Counted that way, apparently empty space is crowded. A cubic centimetre of the present universe contains, on average, About 411 cosmic microwave background photons. A room-sized volume contains an enormous number, passing through matter and through our bodies with almost no noticeable effect. They outnumber the baryonic particles of ordinary matter by roughly 1 billion to 1. Their gentleness comes from the energy of each photon. A 2.725 Kelvin blackbody distributes its radiation across microwave frequencies. When its spectrum is expressed as intensity per unit frequency, the maximum lies near 160.2 gigahertz, corresponding to a wavelength around 1.9 millimeters. Different ways of plotting a spectrum place the apparent peak at different numerical wavelengths or frequencies, but all locate it far outside vision. Calling this sky blindingly bright is therefore safe only as a metaphor for coverage or detector response. The CMB arrives from essentially every direction, and a suitably tuned radio instrument sees an intense, unavoidable background relative to many faint microwave sources. It would not burn an eye, illuminate a landscape, or carry anything like sunlight's energy flux. Numerous low-energy photons and high visual brightness are not the same quantity. That distinction deepens the paradox rather than weakening it. The classical bright sky argument predicted high surface brightness from stellar temperature photospheres. The real universe instead supplies almost complete angular coverage at a temperature only a few degrees above absolute zero. In one sense, every line of sight really does end in an ancient luminous surface. Expansion has cooled and redshifted that surface until its radiation belongs to microwave astronomy. Optical blackness is consequently both physical and observer-dependent. It is physical because the visible and total stellar backgrounds are genuinely dilute. A better eye would not find a sun-like photosphere behind each gap. It is observer-dependent because our narrow spectral window excludes the most numerous photon population around us. Darkness is not simply an error of biology, nor is it pure emptiness. It is the visual appearance of a cold, expanding radiation field whose dominant photons sit beyond the retina's reach. Our eyes occupy that narrow window for local reasons. Sunlight reaching Earth's surface is strong in visible wavelengths, and the atmosphere transmits much of that band while blocking or absorbing large regions elsewhere. Evolution shaped retinal pigments to use photons that were abundant, energetic enough to drive chemistry, and available in the environments where vision mattered. It did not shape us to map a 2.7 Kelvin microwave bath. A hypothetical organism with biological microwave vision would face practical difficulties. Millimeter waves require antenna-like structures and carry too little energy per photon to trigger the same molecular reactions as visible light. But a technological observer can translate them, assign visible colors to measured microwave temperatures, and the apparently black spaces become a detailed image of the infant universe, with small fluctuations marking the seeds from which later galaxies grew. The optical and microwave skies therefore tell consecutive parts of one history. The CMB shows matter and radiation near the transition to transparency before stars. The extragalactic optical and infrared background some later, nuclear burning and dust re-radiation. Expansion links them. It cooled the primordial background, redshifted distant stellar light, and reduced the energy density of both. Human vision samples only a small interval within this layered spectrum. This synthesis avoids two equal mistakes. The first is to call space empty because it looks black. The second is to say darkness is merely subjective because invisible radiation exists. Instruments confirm that today's cosmic radiation field is cool and dilute compared with a stellar photosphere. Biology determines which portion receives the label light, but cosmology determines how much radiation occupies each wavelength, and why. Once darkness is treated as a spectrum rather than a color, it becomes quantitative evidence. The exact CMB shape tests thermal history. The weaker optical and infrared glow counts accumulated stellar activity. Even photons too energetic to belong to either background can be changed by crossing them. The black sky is no longer simply the outcome cosmology must explain. its carefully measured faintness becomes a tool for measuring the cosmos itself. To measure darkness, astronomers often study a photon that seems to have nothing to do with night vision. A gamma ray emitted near a supermassive black hole may carry hundreds of billions of times the energy of an optical photon. It can travel for billions of years. Yet the faint optical and infrared background along its route can prevent it from reaching us. The interaction is pair production. If a sufficiently energetic gamma ray meets a lower energy background photon with the right combined energy and angle, the two photons can become an electron and a positron. Space is transparent to some gamma ray energies and distances, but progressively opaque to others. The pattern depends on how many background photons occupy each wavelength throughout cosmic history. Telescopes such as Fermi's Large Area Telescope observe spectra from blazars and other distant gamma-ray sources. Their intrinsic emission must be modelled with care, because a source can curve or fade on its own. Across many sources and redshifts, however, a systematic energy-dependent suppression reveals absorption during transit. From it, researchers infer the density and evolution of the extragalactic background light. The accumulated ultraviolet, optical, and infrared radiation associated mainly with stars and dust. This is a measurement made partly by missing gamma rays. Direct observations of the diffuse background face bright foregrounds, especially zodiacal light. Gamma ray attenuation offers an independent route because the cosmic photon field leaves a calculable shadow in remote high-energy spectra. The method has uncertainties in source, physics, and galaxy evolution, but agreement with galaxy counts helps restrict the allowed intensity. The exact blackness of the sky is therefore not captured by one brightness number. It is a spectrum that changes with epoch and determines how transparent the universe is to other light. By combining direct backgrounds, resolved galaxy counts, and gamma-ray absorption, astronomers test how much energy stars released and how expansion carried it to us. Darkness has become a target, a filter, and a ruler at once. What that ruler measures is not a literal ratio between light and nothingness. Astronomers compare the background's intensity and spectrum with models containing a cosmic expansion history, galaxy populations, stellar birth rates, dust, and stellar evolution. Each ingredient leaves a different imprint, so the fit is a network of constraints rather than a single solution read from blackness. Blue and ultraviolet background photons are weighted towards short-lived massive stars. Near-infrared light preserves contributions from older, cooler populations. Dust removes part of the ultraviolet and optical output, then returns the absorbed energy in the infrared. A successful history must account for both sides of that transfer without inventing more total stellar energy than the available baryons and fusion efficiencies allow. The integrated background can therefore expose galaxies too faint for individual catalogues and check estimates of how much stellar mass formed. Geometry and expansion enter because redshift changes photon energy, and because cosmological distances convert intrinsic luminosity into observed flux. The same source history embedded in a different expansion history would produce a different present background and a different gamma-ray optical depth. In practice, these data usually complement stronger geometric probes rather than determine cosmic curvature or dark energy alone. There is also room to search for light not made by stars. Some hypothetical dark matter particles could decay or annihilate into photons, adding a diffuse spectral component. Measurements of X-ray, gamma-ray, optical, infrared, and microwave backgrounds can limit such processes when no excess with the predicted shape appears. These limits depend on the particle model and on ordinary astrophysical foregrounds. Darkness does not impose one universal bound on dark matter. The important result is an energy inventory, resolved galaxies, diffuse backgrounds, stellar mass measurements, and high-energy attenuation broadly describe a cosmos in which ordinary stellar populations can account for most of the extragalactic optical and infrared glow within uncertainties. Whatever additional components remain possible, they must fit inside the measured faintness. The unused black between sources is thus active scientific territory. It is the narrow allowance within which hidden populations and unfamiliar physics must reside. The historical reversal is striking. Kepler could use darkness only as a logical objection. An endless stellar universe ought to look different. Later writers sharpened the contradiction, but they could not measure the tiny residual between stars or place it across a reliable cosmic timeline. Blackness was chiefly a boundary condition for philosophical models. Modern instruments divide that apparent blank into components. Photometers measure surface brightness. Spectrometers sort energy by wavelength. Galaxy surveys count resolved sources. Microwave maps recover a thermal relic, while gamma-ray spectra reveal lower-energy photons indirectly. Each method has different foregrounds and errors. Their overlap turns a vague absence into a cross-checked photon budget. The information often resides in departures from simplicity. Minute CMB temperature fluctuations encode the density and motion of the early plasma. A bend in a gamma-ray spectrum constrains intervening background light. A mismatch between integrated galaxy counts and diffuse brightness could point to missed faint galaxies, poorly modelled dust, foreground subtraction, or a new source. Even a non-detection sets an upper limit on what darkness may hide. Calling the black sky one of cosmology's most powerful probes needs perspective. It does not outperform every supernova survey, gravitational lensing map, or acoustic scale measurement. Rather, backgrounds are powerful because they integrate processes otherwise dispersed across immense distances and times. One field of faint radiation carries the combined record of stellar burning, dust processing, expansion, and potentially exotic particle physics. The cognitive shift is from asking why information is absent to asking which histories are compatible with the small signal present. Perfect black would itself be a measurement. A weak glow is richer because its spectral shape and interaction with other photons add dimensions. Darkness has error bars, foreground models, and redshift evolution. That makes the night a record rather than a curtain. Its present entries describe a universe 13.8 billion years into its development. But a record also has a direction. If expansion and stellar activity continue along the trends we measure, the photon budget will not remain fixed. Today's black sky contains the initial conditions for forecasting a darker future. Forecasting begins by separating light already in transit from light not yet made. Today's extragalactic background contains photons released throughout past stellar history. As the universe grows, those photons continue to redshift. Each carries less energy, and their number per physical volume falls as space expands. With no new emission, a freely traveling radiation energy density declines rapidly, approximately with the fourth power of the scale factor. New emission partly replenishes the field. Existing stars continue to shine, and new ones still form. But the observed decline from cosmic noon indicates that replenishment is weakening. Gas locked in long-lived stars and remnants, heated in halos, or expelled from galaxies is less readily turned into fresh stars. Detailed forecasts depend on uncertain astrophysics, especially over times far longer than observations cover. Yet no known trend supplies an eternal constant luminosity density. The CMB follows an even cleaner rule. Its temperature falls inversely with scale factor, so its photons shift to ever longer radio wavelengths, and its energy density fades as the scale factor to the -4th power. Local sources and detector environments will eventually overwhelm this relic long before its photons cease to exist. Expansion also changes which regions can ever send new signals. The particle horizon, the domain whose past light has reached us, can continue to grow in comoving terms, while an accelerating universe also possesses a future event horizon. Beyond it, light emitted now or later will never arrive here. These two horizons answer different questions, and the future one prevents an unlimited supply of newly emitted distant light from replenishing our sky. Thus, the measured photon budget does more than describe the present. Its spectral redshifts, declining source rate, and cosmological dilution specify the directions of change. Diffuse backgrounds cool, thin, and become harder to detect. The far future is not simply today's sky with fewer stars. Its accessible universe will be reorganized by a boundary in causation, leaving gravitationally bound neighbors visible, while much of the current extragalactic scene slips beyond communication. The change is already underway, although no human lifetime can watch its grand result. Measurements of distant supernovae and the cosmic expansion history show that the large-scale expansion has been accelerating for several billion years. In the standard lambda CDM model, a component described by a cosmological constant dark energy comes to dominate the future dynamics. Acceleration does not tear apart every structure. Atoms, planetary systems, galaxies, and sufficiently bound galaxy groups remain held together by local forces. The separation grows mainly between systems that are not gravitationally bound to one another. The local group, including the Milky Way and Andromeda, belongs to the protected population. Most distant galaxy groups do not. The relevant boundary is the cosmic event horizon. At any observing time, it marks the greatest present distance from which a signal emitted then can ever reach the observer in the infinite future, given the assumed expansion history. It is not simply a wall moving inward through nearby space. In a universe approaching exponential expansion, its proper radius tends toward a roughly constant scale, while comoving coordinates enclosed by it shrink. More galaxies occupy comoving positions from which newly emitted light can never catch up. We can still receive older photons from some of those galaxies. Their crossing of an event horizon is not a visible instant when an object suddenly disappears. Successive signals arrive increasingly delayed, red-shifted, and faint. The image seems to freeze toward an ever earlier state while its energy drains beyond practical detection. Forecasts over hundreds of billions of years depend on dark energy retaining the properties inferred today. If it evolves, the horizon and timescales could change. Under lambda CDM, however, the broad outcome is stable unbound regions become causally inaccessible, relic backgrounds cool, and the sky available to local observers loses its distant structure. Cosmic darkness deepens not because space runs out, but because acceleration progressively limits which parts of it can continue to speak to us. While those remote voices fade, the local group will continue its own evolution. The Milky Way and Andromeda are gravitationally approaching and are expected to interact in roughly 4 to 5 billion years. Though the detailed timing and the Sun's eventual orbit remain uncertain, over subsequent encounters, their stellar systems will likely settle into one larger remnant, sometimes informally called Milkomeda or Milkdromeda. The name can suggest a single brilliant collision, but stars are so widely separated that direct stellar impacts should be rare. Gravity will reshape orbits, compress some gas, and may stimulate periods of star formation. Later, as gas is consumed or heated, the remnant will age. Smaller local group galaxies may merge with it, or remain as bound satellites before longer-term interactions alter the system. Beyond this island, galaxy light will be carried to longer wavelengths. A spectral line once optical will pass into infrared, microwave, and radio bands. Photon arrivals will spread farther apart, and flux will fall. A sufficiently advanced receiver could follow signals beyond the point at which a human eye or present telescope loses them. But no finite instrument can defeat unbounded redshift and vanishing arrival rates indefinitely. Saying galaxies cross the horizon therefore compresses two stories. New light emitted after the event horizon boundary can no longer reach us. Older light already on its way continues arriving in an increasingly stretched sequence. Operationally, the galaxies fade from detectability causally. Their later history becomes inaccessible. After tens to hundreds of billions of years under standard assumptions, Observers in the merged local group may see no external galaxy. Their sky will still contain local stars for a very long time, especially low-mass red dwarfs, along with remnants and transient events. But the grand web of clusters and voids visible to us will be absent. The local remnant will seem less like one member of a vast evolving cosmos, and more like a solitary stellar island surrounded by an observational sea with no reachable shore. For astronomers on that island, the missing shore would be more than an aesthetic loss. Nearly all galaxies available for a Hubble diagram would be gone. Stars within one gravitationally bound remnant would not participate in the cosmic expansion, so local motions would offer little evidence that space on larger scales is still stretching. The cosmic microwave background would also retreat from practical reach. Its temperature and characteristic frequency keep falling as the universe expands. Long before the photons vanish mathematically, their wavelengths may exceed useful observing scales, and their signal may be buried beneath plasma effects, local radio emission, or fundamental horizon-related backgrounds. Reconstructing a hot early phase from that relic would become extraordinarily difficult. Primordial element abundances in the ages of local stars could preserve clues. A sufficiently creative physicist might infer that the island had a deeper history, and no theorem says future observers must be unable to discover the Big Bang. Yet the direct, mutually reinforcing evidence available now, external galaxy recession, large-scale structure, and a clean CMB would be drastically diminished. Their simplest empirical cosmology might describe one old, apparently static stellar system embedded in otherwise empty space. This is an inversion of the earlier paradox. 17th century thinkers saw a dark sky and debated whether stars extended forever. We can resolve the question because our sky contains galaxies at many distances and a primordial microwave field. Future observers may again face darkness with fewer means to learn that an immense population once lay beyond it. The darkness would not prove their cosmos static, just as ours alone does not uniquely prove every feature of modern cosmology. It would reflect an observational horizon shaped by their epoch. Knowledge depends not only on intelligence and instruments, but on which signals nature still permits to arrive. So cosmic darkness never achieves a final triumph in any purposeful sense. It simply becomes more complete as evidence redshifts away. The surprising privilege of the present is not that we escaped darkness, but that enough faint light remains within it to reveal both a luminous past and the mechanism by which that evidence will fade. That temporary access places us neither at the center of space nor at a specially intended moment. It places observation inside history. We live after the universe became transparent and after generations of stars built the elements needed for planets and biology. Yet early enough that remote galaxies and the microwave background remain measurable. The window is contingent, not designed, but it is scientifically generous. The darkness around its signals is part of what makes them legible. If stellar surfaces covered every direction, there would be no cool world from which to study them. Instead, finite age limits the light that has arrived. Expansion reduces its energy and shifts its wavelength. Stellar populations burn finite fuel at changing rates. Cosmic acceleration will eventually remove most unbound galaxies from view. The black sky is the combined appearance of those limits. It is not absolutely black. Optical and infrared backgrounds retain the integrated work of stars and dust. Microwave photons preserve the early plasma. Tiny fluctuations remember the beginnings of structure, while missing gamma rays reveal the intervening glow. Darkness provides the contrast, but the faint radiation within it carries the history. The original question therefore changes meaning. Space is dark even though the universe contains countless stars, because countless is not the same as eternal, uniformly shining, or causally accessible. Distance alone never solved the puzzle. Time, evolution, finite fuel, and expanding geometry do. Human eyes then render their cool, spectrally shifted result as black. Far ahead, the visible archive will contract. Nearby stars will endure for immense intervals, then they too will change, while diffuse backgrounds continue to cool. For now, a moonless night still offers both sides of the evidence: bright points from local and distant furnaces, and broad, dark intervals that tell us those furnaces have not filled eternity. The darkness is therefore not a void opposed to the universe. It is the quiet form taken by a universe with a past, an evolving population of lights and a horizon. Looking into it, we are seeing not nothing, but the shape of cosmic time.